Ladies and gentlemen, welcome to the ICE Technical Meeting, Forensic Engineering and Case Studies. This event is brought to you by the Institution of Civil Engineers. My name is Benjamin Ryan, and it is a pleasure to act as your master ceremony in this event. Before we start, allow me to read the rundown of our event this evening. First, I will be reading the rules of the webinar. Second, there will be opening remarks by the chairman of ICE Jakarta Local Association, Phil Woodmansey. After that, the event will be guided by Mary Natalia as our moderator to start the presentation of Ian Petrich. The event will then continue with a Q&A session. Ladies and gentlemen, for your own convenience, please pay attention to the following rules. You can submit your questions for the speaker by pressing the raise hand feature located at the bottom of the screen. The questions should be in English. You can raise your questions before, during, and after the presentation of the speaker. Now, I would like to invite the chairman of ICE Jakarta Local Association, Phil Woodmansey, to give his opening remarks. To Phil Woodmansey, the time is yours.
Okay, thank you, Ben, and welcome everyone to our ICE Jakarta Local Association technical presentation tonight. Welcome to all our colleagues in Indonesia, and I think there's a few people joined from overseas as well throughout Asia. So, welcome everyone. It's great to have you on board, and welcome to Ian, who's I only met for the first time tonight, so it's good to meet you, Ian. And Ian will be talking to us tonight about forensic engineering with some case studies. Forensic engineering is a very specialist discipline of civil engineering, and it requires very special kinds of people. People that are very good at working with detail, very methodical, and they also have to be very good communicators. Often they're called upon to explain very complicated issues to people who don't have the necessarily same technical kind of background. And it goes without saying that the people that work in this type of field also have to be very technically excellent. So I think after listening to Ian, you'll see a lot of those traits. I've only met him tonight, as I say, and I can see that he's a very good communicator. So I'm really looking forward to his presentation. So I will now hand over to Mary, who's going to be our moderator tonight. Enjoy your evening.
Thank you, Phil, for your introduction. Right now we are having Ian Petrich live from UK. I will read some biography of Ian. Ian is holding a Bachelor of Engineering, Master of Science and Engineering, and then also Master of Mechanical Engineering. Ian is internationally recognized as a technical authority for the structural integrity, failure investigation, and asset management. He also has 30 years of experience working for world-leading technology companies in offshore and onshore oil and gas and power generation. Several companies he's working with is GE, Cavalier, British Shipbuilders, and the Welding Institute. Ian also has worked for nuclear submarines, which is pretty cool, hydro dams, thermal power station, transmission pipelines, refinery, and tank farms. Ian currently is the owner and the director of IX Solution, both in Malaysia and UK. Ian conducting his work, integrity management assessment, and failure investigation worldwide. Tonight, Ian will be presenting highlights in common damage mechanisms affecting engineering structures. And then he will be presenting two case studies, which is Alexander Keelan offshore platform and M.W. Kurdistan. These case studies will be used to indicate the failure mechanism, investigation procedure, and then the resulting conclusion. Pak Ian, the screen is yours. You have 1 hour, and then after that, we will continue for Q&A. The participant can write the questions or raise your hand to mention your questions. Pak Ian, the screen is yours.
I'm assuming everybody can see this.
Yeah, it's clear.
Thank you very much. Thanks very much for inviting me. I'm going to spend the next up to an hour talking about the darker side of engineering when things fail. We learn a lot when things fail. In fact, the whole engineering field is based on us learning from things breaking. And some of them are classic. And I'll talk about some of them that affected industry. My time through my career, I accidentally got into this area. I worked for GE, British shipbuilders, and I was always dealing with heavy structures, old structures. And this is led to me getting involved in this forensic area. What I'm going to talk about, I'm going to set the scene a bit initially, and I'm going to talk about damage. What type of damage do we expect to see? Then, what is a failure investigation? And then root cause. What is root cause? And then I'll talk about Kurdistan and Keeland and a few other failures as we go through. To keep it to within an hour, I'm going to be talking about metallic failures, so steels, and primarily steels, just to make it easier to handle. What you see on the screen now is information that's publicly available. You can Google Marsh Research, and they list every year or every other year the top 100 or top 10 failures and how much they've cost. And they split it down by industry areas. So here we're looking at refinery property losses from 1978 to 2017. So in 1978, as we go round, clockwise round, you can see we're looking at about 100 million US as the largest property loss on a refinery. As we come round, so by 1998 and 1988, we're starting to see a few more year-on-year failures. We get into the 2000s, and we're getting more. Not only are we getting more, they're getting more expensive. And as we come up to present date, we're starting to see this occurring again more frequently, and the values are starting to go past $1,000 million. So $1 billion if you're UK, or 10 billion if you're US. These values are getting very, very significant. Here I'm talking financially. Unfortunately, normally associated with these numbers are people's deaths, so fatalities. So understanding why the failures occurred is important to make sure that it doesn't happen again. So what we're seeing here is just some data from the US. They're looking at their transmission pipelines. And what you can see is here, it's from 1998 up to a reasonably pleasant date. It's what appears to be a trend of growth of losses in financial terms. There's a few things to be watch out for here. One is that the asset base is growing. There's more and more pipelines around the world, or more and more pipelines in the US. Also, they're getting older at the same time. So they're putting more pipelines in and they're getting older. So this data is got to be taken in with that. It looks like it's getting more and more failures every year, but we've got to take in the fact that there's a lot more equipment out there year on. So correlating between loss and age is not easily predictable. If you want to try and get hold of data like this, it's available, but you will find the US, the UK, Canada, some parts of Europe are the only countries that seem to be collating this at the moment. And we'll see this hopefully pick up in other countries as it goes along. And it's the regulators that drive this. So in the UK, the Health and Safety Executive, in the US, or OSHA, these are the people trying to get a handle on what's occurring when things fail. The problem with failures is they're unexpected. If they were expected, we'd do some form of preventative maintenance. We're looking here at a hydropower penstock failure. This was in Switzerland at Clousson-Dixon hydropower station in round about Christmas 2000. And here we had they had a new pipeline, a new graded pipeline put in, new material, and one evening they had a phone call saying that there'd been a landslide and that the hamlet to the side of the penstock had been washed away. And what had occurred was there'd been up at this part of the penstock on the hydropower station, there'd been on the longitudinal seam weld, there'd been some cracks during fabrication. It'd taken a while, but these had grown slightly due to a small amount of fatigue, and released water into the soil. So it hit a point which caused a landslide and unfortunately hit the hamlet underneath. This investigation took 3 years. It ended up not going to court, but it was very public. Unfortunately for Switzerland, which is not a country known for disasters, they had 3 in a very, very short space of time. And this was the first one. Then they had a train disaster. It was very, very public. The lesson learned here was the material and the welding was the issue here. They'd used stronger material to have thinner sections, which is cheaper because on a rate per ton for the material. So the root cause here was a design issue, design and material selection issue. If you want more information on this, I've put a link to some public information that's available. The other thing about recent failures is, well, recent as in the last 20 years, is a lot of them aren't very well publicised because they're still normally going through some form of arbitration or legislation effects. So I'll be talking more on failures that are a little bit older. The big question when it comes to damage and how things fail is very simple. How would this piece of plate fail? If this was a piece of plate with a tensile pull on it, how could it fail? Normally I'd ask this, but I'd ask a classroom of people to answer this. Obviously, a webinar, it's quite difficult. First is the plastic type of failure, which is what at degree level and college level we're taught that we're designing to allow for, so it doesn't get overloaded, so the material properties don't get overloaded. So one way to fail is to actually increase the load till it fails. The other way is to reduce the section by metal loss, either by corrosion or by things like erosion or mechanical removal of the material. Things like external interference. So any of you that are in the transmission pipeline industry, external interference is a big issue. So you're reducing the section, upping the stress and overloading the section till failure occurs. This is one of the big areas of concern for the refining industry. It's a good example where they've got lots of metal loss on their equipment, and it's one of their number one failure damage mechanisms is metal loss. Cracking is another issue. So you get a crack. So you get a crack either on the surface or subsurface growing due to some mechanism. It may be stress corrosion or fatigue or creep. And this crack grows to a depth when the material's toughness cannot resist it. It can't resist the intensity of the crack tip anymore. And it fails either brittly due to it being a brittle material, or you get ductile tearing due to the material having a good level of toughness. The other thing that happens is that there's two mechanisms when it comes to cracking. One's the crack trying to drive forward. The other is the remaining ligament, a bit like metal loss, where there is, you can imagine it like metal loss, it's just overloading of the remaining ligament. Another way it could fail is metallurgically. Now, this is the hardest generally to predict. It tends to be the hardest to inspect for. But what you get is the environment attacking your material. Now, this can create a crack. It can age the material. It can embrittle the material, so reduce its toughness. It could reduce the corrosivity, resistance of the material, or it could change the tensile properties. Probably the most common that we see is it reducing the toughness of the material. So the graph that I'm showing here is your Sharpie transition curve. For those of you who, if you do the Sharpie test a number of times over a different temperature, for most steels, for most ferritic steels, you'll get a shape like this. And the material goes from being tough to being brittle. And what happens is if you get environmental embrittlement, you move this curve. So the temperature increases. So where before you needed to be maybe in cryogenic application, you've moved it such that it could happen at room temperature, go from being very ductile to being very brittle. And again, you have some sort of pre-existing flaw or just a defect, and you've reduced the toughness that far that it just fails and overloads. There's lots of different damage mechanisms, but they all relatively fall into the same categories of types of damage. And the standards bodies have come up with these definitions of different types of damage. So you get surface connecting cracking, so imagine a fatigue crack, subsurface cracking, so you've got a crack in the body, so it's something like creep crack there, and microfishing, microvoid formation is interesting. That's creep and some others. What you get over time, you're getting the grain boundaries of the material, microvoids occurring. You get initially isolated cavities. Then these cavities start orientating towards a perpendicular stress direction. These cavities then link together, become a micro crack, and then they become a macro crack. So you're seeing this here. In creep, if you see any cracks, that's the end of life. Even very small ones. Metal loss due to erosion, corrosion, metallurgical changes, what we've been talking about. And then there's mechanical damage itself, where you get gouges, dents. It's understanding, the major part of the failure investigation is understanding what damage occurred, when it occurred, why it occurred. They're the three big questions you're asking yourself. So here you can see fatigue, which has a very much a classic failure phase, where you can see the initiation point, and then as the crack slowly extends through the thickness, a bit like a tree ring. So if you cut a tree, you'll see rings, and you can see what are called beach marks. These normally are associated with something during operation, so it could be a shutdown. It's a good example. The type of cracking here shown is stress corrosion cracking. You need a poor combination of material, environment, and stress generally for stress corrosion cracking to occur. A classic one is chloride stress corrosion cracking, where stainless steels, they don't like chloride. So stainless steels in seawater is very poor, but they need stress, they need high stresses, yield-like stresses, and you get this crazed like cracking. Not always crazed cracking, but quite a lot of them are crazed cracking. The very bottom picture is interesting. I like showing this to young graduates and young engineers. All these types of defects that are shown, or damage that's shown here, are due to corrosion. So when people design things and put a corrosion allowance on, they're assuming something a bit like this. However, that type of damage is relatively rare. Most corrosion damage is more like these two. However, you can get some that are very, very sharp and act more like cracks till you get to a point where they are cracks. Now, these are created by corrosion. You don't think of corrosion generally as a cracking mechanism. And people do get confused, and these things do catch people out. Now, fortunately, for over the years, mankind hasn't been very good at predicting damage mechanisms. They're very good at identifying them after they've happened. So when people design something brand new for the first time, generally they've had problems. A good example of this is the ships during the Second World War that went across the North Atlantic between the UK and America. They'd suddenly gone from riveted vessels to welded vessels, and the Liberty ships, as they were called, were snapping after a short period of time as they were crossing across the Atlantic. Again, the fatigue coming out of welds. Interestingly, that's where my ex-company, the Welding Institute, was devised, because they wanted that solving. So we spun out of Cambridge University to answer that question for the UK Admiralty. But there's lots of information about damage mechanisms. A recent publication by the American Petroleum Institute, 571, lists quite a number of damage mechanisms for refining equipment. Now, the advantage here is there's a big section just on general damage mechanisms that affect all industries. And it's a good collection. It tells you what it looks like, what type of materials, what are the damage drivers. It's a good document. ASME and the American Society of Mechanical Engineers produced their post-construction code standard. And in one of them, number 3, which is about risk-based inspection, they've got a whole section on damage mechanisms. The American Power Research Institute, in their boiler tube failure manual, has a very good section on different damage mechanisms. They've also nicely written how to go through a failure investigation in there. Things like the Welding Research Council bulletins, they've got some on pulp and paper, transmission pipelines, and there's other documents and books available out there. Depending on your industry, that there'll be something somewhere. I show this slide quite regularly. Most damage mechanisms are time-based. So corrosion is metal loss over time, as an example. Fatigue is not. Fatigue's about changes in load or changes in stress. It's about cycles and the range of those cycles, not time. Just to get everybody thinking that way, fatigue's an odd one. There's another one that's worth knowing about and understanding is liquid metal embrittlement. It's rare, fortunately. And the most common example of it is aluminium and mercury. If you took some aluminium and you drop mercury onto it, so the mercury is liquid, so room temperature, it will crack the aluminium instantly. These are 2 damage mechanisms that don't act. So fatigue, liquid metal embrittlement, don't act with a time basis. And just to be careful if you ever come across them, to understand them. So a typical failure has a few stages. There's the initial damage initiation. So it could be a well flaw. It could be a poor profile due to and cause a stress raiser. It could be paint breakdown to allow atmosphere, so for external corrosion. It could be paint breakdown. Now the atmosphere can touch the outside or the metal. Then you normally get some form of growth, be it fatigue, stress corrosion, cracking, these type of mechanisms. Obviously, there's the one thing I'm not addressing here is event damage or mechanical damage. But these are the stages otherwise. And then finally you have a failure event, either due to some sort of brittle fracture, rupturing, ductile failure, or leakage for those in the pressure industry. They're the typical stages. Something occurred to start the damage, it then grows, it then fails. Now, that can be very, very quick so like an event. So you get a ship hitting another ship. You will get these occurring. So you will get damage initiation, subcritical growth, and rapid failure, but it'll occur in seconds. Whereas in most engineering structures, these tend to take a bit of time. Why do we do failure investigations? For the vast majority, everybody listening, I hope we all understand, we want to know why it happened. We want to learn lessons. We want to make sure it doesn't happen again. But there are some hard and fast reasons. A lot of companies have procedures within their integrity management system that says, or the health and safety systems that say, if we have a failure, we will investigate. Another big one is insurance. Who's going to pay for the damage? Who's going to pay for the cleanup? Who's going to buy the new equipment? And you tend to find in insurance policies, there's one sentence that everybody's arguing about for years, and it's all about who pays. The insurance companies don't want to pay. They're quite happy to take your they're quite happy to give you the insurance coverage, but they want to make sure that you weren't, or the company wasn't at fault before they pay out. Regulation, certain countries have regulations that say if you have a failure, you will investigate, you will inform us. Legal disputes, so expert witness type, and public pressure. We've all seen failures around the world, really big ones. The public pressure is quite large. The scope of these type of investigations can be very small, from a small piece going and it just needing replacing, to multi-million-dollar, multi-billion-dollar, multi-fatality investigations. Probably the most famous or the most fatalities ever was Bhopal in India. It's still going on today. Roughly around about 4,000 people were killed, and over 500,000 people have been affected by it, so long-term health issues. These are the things that have got to be addressed. Why are we doing the investigation? How big's the investigation? These are some information from the UK offshore industry. The UK HSE and others hold this sort of data, failure data. So this is hydrocarbon release rate, so pressure equipment that's released. And they've broke it down into two areas. There's a software, which is people and procedures, the reason for the failure, or hardware, so fatigue, vibrations, so the metal broke for some reason. And the split's about 1/3 to 2/3, approximately. So mechanical damage or damage to equipment, and the other third, the failures were caused by an operator error or something like that. What's really interesting is when you look at the underlying causes, so the root causes. So if we look at hardware, inadequate inspection and monitoring. So they weren't looking after the equipment as it got older, or they didn't know it was going to fail. Inadequate design. So it was never designed correctly in the first place. Now, So of all the failures, 2/3 of them are down to equipment, and approximately 1/3 of that 2/3 is due to it never being designed correctly in the first place. When it comes to software, the two underlying causes are the people, more people-ish. It's down to inadequate procedures and then inadequate compliance. So even then, they've got the procedures, they're just not doing the procedures. It's interesting looking. So we're talking about root cause here. What caused the damage, what caused the failure, and what is the real underlying cause. A failure investigation has a relatively generic process, regardless of which industry you're in. I have had the horrible thing of photographs come into my email box. We've had this failure and there's bodies lying there, and they say, what should we do now? We've got rid of the fire, what should we do now? You're trying to preserve the failure as much as possible. In a lot of cases, people want to repair and get back up and running and making money again. If you want lessons learned, you want to have time, and you want to preserve the failure. So you normally do an immediate site visit. Obviously these days, a lot of it's done via Zoom, but this is what you're doing. Then you do a detailed site investigation. Once all the debris has been moved out and things like that have cleaned up, you can do a more detailed site investigation and relevant data gathering. So things like design information, inspection information, things like this. You would then take samples for further laboratory examination. So if you had a leaked transmission pipeline, you would probably take that leak section away. Then, given all the data that you've accrued to that point, you would create some hypotheses, and then from that, determine the most highly probable. Now, it may mean that you end up doing some tests to prove, depends on how big the investigation is. You might do something like finite element analysis to prove that these loads could be there. These type of studies may be spun out to prove the hypotheses. And then you want to determine the root cause of failure, which is different to the failure mechanism. A good example, when I was a young engineer, which is a while ago, I got told a story about a hotel in the US, a very famous hotel in the US, and they were having problems with their room service, getting the meals to people in the rooms late, and they would be cold. And so the failure was the food turning up late. The root cause, when they really looked at it, was the fact that the bedding for all these rooms also used the same list as the food, and it was slowing everything down. So the root cause was actually having having the bedding using the same lift as the room service for food. So the lesson learned was we need to get the bedding away. We don't want to mix them. So they started on each floor having bedding, store on each floor, and it was over. So the root cause is not the same as the failure mechanism. And it's very interesting. Well, it's important that distinction's made. And the most important thing about a failure investigation, and something that gets missed, is the dissemination of the lessons. Some companies I've seen have been very good about it, and some companies don't. They say they're going to disseminate, they don't. They don't really want to talk about failures or where the company might have done something wrong, so they don't disseminate, which is unfortunate. The things like EPRI document have their steps, so they're on about identifying failed or degraded tubes, then go and have a look at the tube, do some photographs, bring it back to the lab and perform a lot of tests, and then finally prepare a document. So there are these process flows around if you're ever needing to have one. Detailed site investigation, these are interesting. And data gathering. The typical data records you want are design calcs, drawings, internal, external environment information and how it's changed over the years, historic inspection and maintenance, loading, operation, especially at the time of failure. The other things to be careful of with the loading operation is what happens during shutdowns or some transient events. Historical loading, interviewing of personnel, especially the people who were there that day when it happened. Any management of change records as well. And the most important thing at this point is the terms of the reference. Why is the investigation being conducted? Is it to help with an insurance claim? Is it to learn lessons and make sure it never happens again? Everybody will say, oh, it's all of that. And that's true. However, when you write your report or when you start disseminating, it's easier to understand if the objective of the failure investigation is to prove that you weren't at liability. One of the big questions that comes along right at the start of a failure investigation is, was it correct at the start? It's a difficult political situation you're in, especially when you're on site. Everybody's got their own theories, which is always interesting. But there's people hiding information, putting up smog screens. So you're trying to make it difficult to work out the truth. So you go to site, you might see something like you do on the left-hand side here. This is a flare tip from a refinery. Very interesting how this damage occurs. But you end up with something like this. And right, okay, I'm going to take this back. Where am I going to cut it? You're going to transport it. You've got to label it. You've got to make sure it doesn't get contaminated any more than it already is. So you might do some preservation on the item. Funnily enough, it is a very complicated creep, stress corrosion cracking type mechanism at the flare tip. Laboratory investigations. This is a typical thing that would happen at a lab. The material will come in, immediately a visual examination would occur and photographed. So you've got the as received condition. Then you would do some non-destructive testing and dimensional measurements. So you might do dye penetrant, you might do thickness checks, you might just do something as simple as get a tape out and measure diameters. You might do clever techniques like phased array, but they would normally be non-destructive. Then from all this information, you will mark up the material for extraction of samples. Now, depending on what you're planning on doing, but sample sizes are generally small in comparison to the whole structure. So a Sharpie sample is 10 by 10 millimeters. Sorry, 20 by 10 by 10. So relatively small. A specimen for a SEM, so a scanning electron microscope, is normally 10 millimeters by 10 millimeters. So you can't do a lot of very detailed investigation in the timeframes that you're on. So you've got to select your specimen areas carefully. Then you would examine the fracture faces. Again, when I was a young engineer, an older engineer, I should say, who would be very politically correct these days about a more experienced engineer told me that the only thing in a failure investigation that's true, absolutely true, is the fracture face. It doesn't tell any lies or try to cloud the situation. Then you would characterize the material property. So one of the big questions is, was the material correct in the first place? Was it fabricated correctly? You want to remove that from the analysis early. If it was created correctly, you want that out of the way. But you want to know what are the material properties, what are going to be the load limit requirements. Then you would carry out metallography. So what you're seeing here, we're getting smaller and smaller and smaller. And you would look at, so here you're looking at a crack front at a reasonable macro size. Here you're at an SEM, so you're down at nano levels. That's the fracture face. And so you're coming down in detail. So you're zooming in more and more and more. Root cause. So you've done all that work, and next you do a root cause. There's quite a few methods. Personally, I prefer fault tree, where you start at the top. So in this case, a pipeline leak at a certain location, and then you look underneath of all the different potential scenarios, and you follow the branches down till you get to the very, very bottom, the root cause. And it may not just be one root cause, there may be a couple of root causes. There's the 5 whys, where you'll get a group of people sat around, and the question would be, why did this leak occur? And you would go down 5 levels of the why. You ask 5 questions as you drill down. Another common technique to use is failure modes and effects. Very good for if you've got a system rather than a component, working out methods down. So most methods will drill down to a root cause or root causes. You would then use your investigation to eliminate or validate any scenarios or issues. The interesting thing about doing root cause analysis is this picture that I've got at the bottom. You're trying to excavate or show the truth, and there's always someone somewhere piling stuff on, trying to cover it for some reason. It never helps. So failure mechanisms of root cause are usually different. Here we've got a pipe that failed, a seam weld where there's a crack, and this crack was generated by stress corrosion cracking at the seam weld. But the potential root cause wasn't stress corrosion cracking. Stress corrosion cracking was the failure mechanism. The root cause was that the pipe bent due to land movement and caused a large, very large over yield stress. So locally it bent, a bit like your ruler. You bend a ruler and the stresses were over yield. The environment got to the steel and caused stress corrosion cracking. So the root cause was the land movement. So because of this, as you can see here, you've got people like me who are involved in the more detail part of it. But in this type of thing, you will have metallurgists, then you have people like me, mechanical, who are more sort of like project management over the top of it. Then you've got the geotechnical people, you've got structural people looking at modelling. So there's quite a lot of people that get involved in these type of investigations. And this doesn't include, I'm talking technically here, I'm not including all the management people that seem to get involved in this. You would normally have a HSE health and safety representative, obviously. Then you get the owners of the equipment. Then you get maybe the insurance people. So this can be quite large teams. Then you original equipment manufacturer. It gets very, very complicated and very political very quickly. Just to go on to some bit more Discovery Channel, just to quickly go through some more classic failures, just to show you how things can happen quite quickly. This is the MV Kurdistan. It's a cargo tanker. It was built in Swan Hunters in Newcastle in the UK in 1973. It was 3 sister ships, and they were relatively large, 32,000 tons. And they were strengthened over the first third, so in this area, with steel for going into ice, in the ice pack. In its history, the bilge keel had been damaged in 1975 and repaired in 1977. And if you want the full details, Steve Garwood's paper can be downloaded. So in 1979, 15th of March, in Nova Scotia, the Kurdistan left Port Hawkesbury and going around Nova Scotia and came into the ice field. At the time, it was carrying 30,000 tons of C6 fuel oil at 140 degrees F. We're in an ice field, so it's below freezing. So the air temperature at the time was minus a degree, roughly. Sorry, the sea temperature was minus a degree and the air temperature was 0. At 12:53 in the ice field, they couldn't go any further. They got about 1.5 miles into the ice field and they had to back out. Roughly an hour later, as they were backing out, a shudder was felt and the bow lifted. And at the time, they had gale force winds and some heavy swelling. And so this is the first shudder. Everybody was running around the ship. Somebody looked over the side. I could see on the port side, more obviously, it was a 1.8 meter long crack, roughly 4 meters below the deck, and it was about 1/2 inch wide. So oil was coming out of this crack. There was one on the other side, slightly smaller. So they pumped the oil from the number 3 tank to the number 4 tank and carried on the way. So they're trying to get back to port. On the a second shudder occurred at 9:30 at night. The oil transfer was stopped. The weather conditions were better, so there was only 2 meter swells in wave height now. And finally, around about 10 o'clock that evening, there was a third shudder. The bow rose and the vessel broke in 2. So it snapped basically right along this point. And these are the 2 parts. So there's the bow and there's the aft. This is the aft when it was brought to port. And so this is at St. John's, New Brunswick. TWI were flown out to have a look at this. And this is the bilge keel. This is the important area. The bow section was sunk on the 1st of April to prevent further pollution. So they only brought the aft section back. So the failure investigation visual, quite a lot of the usual types of that they've been talking about fracture, taking samples to do Sharpies, looking at fracture faces. And what had happened was the fracture initiated at this port, the bilge keel port side. The weld repair, it was not full penetration, and there was a lack of weldment. There was a lack of lack of fusion, and there was an intrinsic defect here, not overly large. What had happened was that it reached a critical size. It started to run to brittle fracture, so it ran out of here and then started going up the sides. So this is a primary initiation, and the cracks ran this way. There was a secondary initiation over here. And this is what it looked like at the bilge keel. So the original defects, the original repair, lack of fusion, is that hatched area, and it fatigued this much. So it hadn't fatigued significant amounts. There was high stress at the time due to the sea conditions, so 6 meter waves. Also, you had 140 degrees F here and 0 degrees here, so you had a differential temperature causing stress here. And once it's reached a critical side, it just zipped across the material. The material acted brittly. What's interesting, if the material has failed brittly, if you look at the fracture faces, chevrons can be seen. And these chevrons point back to the area of failure. So the material testing showed that 20 degrees C, you were getting quite nice, quite high or reasonable Sharpie energies. And then as the temperature dropped, it was significant. Even at 5 degrees, they were getting values of 6 joules. For those of you who don't get involved in this, normally you're wanting 27 joules at your minimum temperature of energy. So these are well below what was expected. So for Kurdistan, it was an original weld repair. It was a weld repair that left a defect in there. So the defect's there. The material was at a temperature where it dropped its toughness, and large stresses were caused due to the waves and the thermal stress across it. Fortunately, nobody was injured. Keelan's famous. You can Google this quite happily, see the BBC and the news reports. This changed the oil and gas industry offshore. So the Keelan platform was a Pentagon semi-sub, and it was in the North Sea. It had 5 columns, so you can see 2 there, there's another 2 there, and there's 1 also there. It had an overall height of 3.56, so it's floating, and it was mounted on 22 meter diameter pontoons. So these columns were onto pontoons. The columns were on the apexes of the Pentagon, and the braces ran between the columns. So there's braces between these under the waterline. And accommodation was mounted onto the deck. It was a mobile drill rig, but it had been converted to an accommodation platform, so flotel as they call them in the industry. And at the time of failure, they had a total of 212 people on board. So on the 27th of March 1980, one of the 5 columns, D, as it was labelled, broke off and the platform capsized. So the minute it broke off, the platform heeled over to 30 to 35 degrees. It took a further 20 minutes for the platform to fully capsize to end up in this orientation. A number of attempts were made to launch the lifeboats. They could only get 2 of the 7 across. This changed the lifeboat requirements on platforms as well. There were 6 to 8 metre waves at the time of failure. For the North Sea, that's not particularly excessive. Unfortunately, 123 people died. This was a major incident. So, post-incident investigation, the platform and the column that had snapped off remained afloat. They took the column to Stavanger in Norway, and divers removed the fractured faces from the capsized platform. Brace D6 is the interesting area, and it has something called a hydrophone support. And it was made from a normal carbon manganese structural steel with a yield of about 355. The brace was 2.6 meters in diameter, and it was about 1 inch thick. And the hydrophone support was a bit like, for those of you working in the pressure vessel industry, it was like a set-on nozzle, and that had a diameter of 325 millimeters. And again, it was relatively thick. It was a set through. And it was just welded on by 2 fillet welds because it was non-load bearing. It wasn't meant to take a load. It was there for attachment. What happened was the brace, the hydrophone fillet weld, had some poor penetration and weld shape and some fabrication cracking. Fatigue crack growth occurred in day 6. It grew till it was 2/3 around the circumference of the brace. And once at a critical size, it cracked and failure of the brace occurred. This then cascaded, and it's shown a lot easier here. So this is column D. This is the one that floated away, snapped off. And here's brace D6. And here you've got this hydrophone, and it's a bit like it's a set-on nozzle, set-through nozzle, with just fillet welds, as you can see here. Very small fillet welds because it's non-structural. It's not structural, it's not a load-bearing part. So it zipped, it cracked there, fatigue grew, it lost that, so the load had to be transported by the other columns, and slowly it cascaded until column D came up. This is an interesting picture because over here you can see the initiating point in 24 months, 36 months, 42 months operation, and then finally fast fracture. So you can see the fatigue beach marks. But what's really good at what's interesting about this photograph is showing you that fatigue crack growth is not linear, it's exponential. Here there was no redundancy, so once you lost one brace, you overloaded the others, and it highlighted to the whole world and the industry the importance of non-loaded weld attachments. Again, it's a very small detail here caused the loss of 123 lives. So to wrap up, because I've probably been talking about too long. Failures occur. There's no way of getting used to it. Man's not very good at eliminating failures, especially when they do something new. There's always something that's forgotten. Failures occur. The numbers are increasing as the population and the age of the equipment grows. So what you're finding now, there's a lot more for companies to talk about integrity management as their equipment gets older, because people want them to go further than the 25-year design life. All failures should have a root cause analysis conducted so that lessons can be learned. How it failed and the underlying root cause are very important. If you're doing a failure investigation, it should be a procedure, follow a plan. Do not assume a failure scenario, then prove it. This happens a lot. Rather, remove factors which are not relevant, so you're left with the most probable reason for failure. People jump to conclusions. We all do. We're human. For those of you who've played board games, it's like Cluedo. You keep going round and round the board until you've removed all the potential issues. Not Scrabble, where you've got a pile of letters and you try and make them into the biggest word you can. Failure locations could be very small details. This is important. And it's very, very rare that a failure is due to one condition. It's normally a few factors all combining. And failure mechanisms are either time or load based. Be careful with that issue. And my last thoughts, and thanks for listening. Quite a lot of the in-service damage mechanisms are not allowed for in the design of equipment. What I'm saying here is your design codes, design standards, try and make the equipment not fail due to overload or fatigue tends to be involved. The other damage mechanisms, they're assuming the designer knows what they're doing. So designing just for stress is not always the safest method. Design codes are not always correct. There's been a big change in quite a few design codes about creep and creep weldments. So understanding your long-term asset and material knowledge is essential. As professional engineers, we should be aware of all the potential failure scenarios that could occur during design, manufacture, transport. Transport's an interesting one. And installation. You know the big blades on the wind power turbines onshore or offshore. Their most critical point is when you lift them, you can actually crack them at that point. And it's actual installation and transportation that's their biggest life damage mechanism. When you're into operations, inspection and maintenance, you in-service damage mechanisms, and then finally understanding decommissioning these days. So you don't cap a well and then it leaks. Thanks very much for listening. I hope you understood me and my accent didn't confuse you too much. Thank you.
Thank you, Pak Ian. Maybe can you open your video for your appearance so we can see our speaker?
Okay.
Yeah.
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 It is open, Mary.
Yeah. So I understood that this very knowledgeable information takes lots years of experience for you. There are two questions here. I believe Pak Armedito Ramadan is working for British Petroleum in Jakarta. His question is it possible to predict if corrosion would be pit type or crack type at a design stage? And maybe based on material, loading, and exposure? Probably you can answer that one, Bapak.
Yeah, actually the answer is yes, because of the number of failures that have occurred in the oil and gas business. So if you're looking at CO2 corrosion, the chances of there being a crack from CO2 corrosion are very, very low. That is metal loss. H2S, because you can get H2S cracking. If you're in sour service, you can get cracking there, but that's normally designed out. And it's normally at welds anyway. So the simple answer there is yes, if you are in a mature industry. So, and the oil and gas industry is quite mature and traditional. So unless you're going, a lot of problems with that at the moment are when they're going deeper, so offshore, and they're now going very deep and ultra deep, then some of them can turn into cracking, but the simple answer is yes.
I saw that Pak Trevor Symes is raising the hand. Maybe Pak Trevor, you would like to ask the question?
Hello, can you hear me?
Yes, we can hear you.
good.
Yeah.
I was interested in your 48% of underlying causes a lack of maintenance and inspection. How much is that due, do you think, to management continually cutting inspection and maintenance budgets as an easy target to reduce costs and meet annual budgets?
Yes, it is. Yeah, I agree. It is that. There's also as things go old. So at the start, say you've got a refinery and it's the start of life. Most of your inspections confirmatory. Yes, we're not having initial very quick issues. So, but they're sticking people's heads that's the budgets. They're then used for following years. So fortunately, with techniques like risk-based inspection that are being used a lot more now, but still the budget stays the same because that's how they do the profit and loss. So where you should be, because your equipment's getting older and you should be doing more inspection, you're doing the same amount of inspection, the same amount of budget. It's quite interesting. You talk to people and say, oh, you buy a car, these plant managers, you say, you buy a car, and after 5 years, you're expecting to do the same amount, or 10 years, you're expecting the same budget for looking after the car as you would if it was brand new. And then, yeah, but they don't care. They're only there for 5 years. Then they move on to the next plant. It's somebody else's problem after they go. And it keeps me in business. Yeah, you can get quite cynical on this side of things.
That's what you say all the time. It's the easy target.
Yes, it is. Very much so it is. Until it becomes a failure. And then everybody's hiding. Well, not hiding. It becomes very political. And it makes people like my job harder. People are coming in, they're trying to, oh, it's not really our fault. We're not going to tell you anything. And then you start, yeah, until there's sat in front of a judge, and then it just gets ripped apart. There are no excuses in front of court, which is interesting.
Okay, thank you.
Again, we have a next question. This is from Mr. Rayhan. Yeah, his question is there any specific welding technique according to prevent the underground pipe corrosion?
Underground pipe corrosion, no. The welding, you pick your welding technique to try and match the parent material's properties as much as possible. There are, I haven't showed all the damage mechanisms, there are a lot, but there is one called preferential weldment corrosion, where if you get that wrong, if you don't get the right welding procedure, you can actually attack just the weld. So you could have a nice bit of pipe that's got no weld. It's been in 10, 15, 20 years. And it's a problem offshore, that they see it offshore, where the weld's preferentially removed due to corrosion, and it's difficult to predict that one. It tends to be as soon as they come up from the well on the platform area. You can do certain things with weldment. Again, it comes down to cost. And what you're finding, to stop that internal type corrosion, people will line the insides. So they'll clad the inside of the pipe. So with maybe something like alloy 625, which is corrosion resistant, or stainless steel or whatever, people will line the inside of the pipe rather than allowing the root of the weld into the environment. So unfortunately, there's no technique that solves that. It would be nice. And if there was, I'd be making a fortune.
Okay, we have another question from Pak Phil, but before that, our attendees here, most of them are civil engineering
Yeah.
students. So could you give them some, how to say, insight how to connect the forensic engineering with the civil engineering, how to encourage them probably, Pak?
Yeah, I guess the example I showed with the, I've got quite a few actually. What the pipeline's a good example that I showed. Now, it's not the only one that I've seen like that. The pipeline, if it moves, the civil movement, so the geotechnical, the movement of the floor, puts a load onto the equipment. I mean, you know, Mary, you would
Yeah.
you've worked on one of these with me. So the interaction between the different disciplines is important. The civil side of things, you're telling us the loading, you're telling us what can change on the structure or on the more local level. It is very important. And this is why you need teams. The bigger, for a small widget that just breaks, yeah, you don't need a massive team. For a transmission pipeline leakage, you need a big team, because there's unless you can spot it isn't geotechnical or civil related, your first question is going to be, is it civil? Is there a civil issue here?
Mm.
So, and it's one of them things where you first go to the companies and they say, oh, how would we do the investigation? And the first thing we ask generally is, well, you're going to need all these disciplines. How much of the budget? Because you're going to have to involve all these different ones. I got involved in, most of my work's all metallic, but penstocks in hydropower stations are a good example of civil mechanical structural interaction, where I got involved in another leak, not the one shown, where the grouting was the real issue. It was the underlying grout. They lost the grouting between the metal and the rock, and it caused a localized area of overstress, just in a very small area. And it was a pump storage scheme, so it had fatigue. So in that local area, they had more and more stress range, higher value, and it caused cracking. There's been a lot of work done on that by what was the old UK CEGB, Central Electricity Generating Board, when they produced the Norwich power station, because they looked at that specifically. They were worried about it. Not that was a problem at Norwich, it was another station. But yeah, there are cranes are another good example. Tanks are a good example. Atmospheric storage tanks, settlement issues on atmospheric storage tanks, very common problem. As the tank starts to tip, go from flat to tip. Now that settlement issue is a major civil. Same with pipe racks on a refinery. It's another good example where you get differential settlement, especially if you've got a refinery that's partially claimed from the sea. So you've got one area that's been reclaimed from the sea and the original landmass, and over time they've changed, and your pipes are taking all that load, and you get joints opening or you get overloading. So yes, there's quite a lot of interaction between the two.
So basically, the deep understanding of material behavior, either it's civils or land and metallurgic, is important.
Yeah. The other issue is you can't. Everybody, we can't know everything.
Yeah.
Obviously, I like to think I do, but I don't. So it's important that you have to have these multidisciplinary teams, like the pipeline. Yes, there's got to have been a large stress there, a very large stress. Where did this very large stress come from? And as mechanicals, we can say, and our civils doing structures, you can say, right, we need a curvature of the pipe of this much. Where did that come from is another civil question, isn't it? How's the land moved? All right. Yeah. So you do need these teams.
Okay. So, Pak Phil, please
Yeah.
proceed with your question.
So Ian, just going back to one of your early slides about failure and the frequency is increasing and the cost is increasing. Is that just a kind of time related thing, or are we getting worse at our jobs?
It's a bit of both. There's a couple of things going on. One, there's a bigger population and it's getting older, so therefore you expect more failures. And at the same time, there's an effort to increase our management of these pieces of equipment, and that's ongoing. And that's how the failure rate at the moment would be a lot higher without that going on. What also is occurring is that we're seeing a generational change in age of engineers. I'm coming up to retirement. Pretty much far away, but that knowledge base is also getting lost as well. So the older engineers retire and take away quite a lot of knowledge with them, and it's never captured. So there's a certain amount of reinventing the wheel every generation, and you have to go through a spike of failures because of it. People talk about corporate knowledge. It doesn't tend to, especially in something like, I guess, the oil and gas game, where a lot of people are contractors. They're just move in and out and move on. Also, there's a bit of a disconnect between the people who operate and look after plant and designers. So your EPC contractors will come in, will design you a brand new power station, build it, and then walk away and go and build another one. So unless failures occur during commissioning or very, very early life, they don't get fed back into the design loop that quickly. And it takes quite a lot of years for that to filter in. I don't know if that really answers it, Phil, but
It does. No, it's I was a bit worried that might be the answer, and you've kind of confirmed it.
if the minute human nature's involved, things. Also, you can look at a good examples. Looking at your mature areas like the UK and oil and gas, say, and America, and so they've learned a lot of lessons over the years about failures, and they've put it all into codes and standards. And new equipment that, say, has been built, say, in Asia, so the Asian engineers haven't seen this development of big due to failures occur. And the technology transfer, if you would, although is that a dirty word these days, that the transfer of that knowledge hasn't happened at the same time. And it's not the Asian engineer, it's not anybody's real fault. It's just, it hasn't happened.
Yeah, thank you.
Pak Ian, we have one question from Ibu Sandra. Please, Ibu.
Oh, hi, Mary. Can you hear me? It's actually Ibu Sandra's husband, because we're listening on one computer.
Okay, will do. Go on.
Ian, that was a really interesting talk, and many thanks for delivering that. I'm a geotechnical engineer, and one general question for you, because I see it maybe as even increasing business in your part of the world or your area, is that we design many structures, especially geotechnical ones, to a certain design life. And I work in the area of geosynthetics, and we design to certain design lives. And I mean, this 100-year design life sounds great when you set off, but as time moves along, more and more of these structures are getting towards the end of their officially designed design life. But it's difficult to imagine after 120 years, we're going to start knocking down all of these retaining walls and bridges and whatever it is. So it seems to me there must be the potential for a whole industry to spring up about reassessing design lives that existing structures have been built to try and decide how much more of a design life they've got beyond the original design life. I hope that makes sense, that question, but it's something that's partly worried me, but also partly intrigued me, because it must be something that's going to be on the increase as the years go on.
Yeah, it depends on your industry. The oil and gas industry and the power industry, because their lives are shorter on their equipment, they already do that life assessment, pushing back the life, because quite a lot of equipment, 90% of it's got plenty of life in it, well beyond design life, because you only design at small locations. You size everything on the most highly loaded area, and that's the area that you got to worry about for life. It's happening. There's a whole new for the mechanicals, I guess. There's a whole new industry sector. Integrity management occurred during the last 20 years. It's gone. There's now sections within companies all about integrity management where they weren't there 20 years ago. So part of the regulatory requirement for some of these structures now is to understand the remaining life of the equipment. And it's quite tricky. I don't know if you've ever watched. There's a program in the UK, Only Fools and Horses, where one of the guys gets an award for having a sweep. He's a sweeper of roads, and he's had the same brush for 20 years, and he gets an award for it. Well, the same brush has had 4 heads and 2 handles. Is it the same brush? And that's what's happening with some of the structures. Power stations, a good example, where they've literally, some power stations, they've ripped out the boilers internally, put brand new boilers in them. It's not the same thing, but it's the same plant. You're right. Hydropower stations are a good example, where their design lives are a lot longer, and the 100 years is when people are thinking, what's the remain? How long can this go? Also, 100 years ago, people over-designed things. Some of the stuff built 100 years ago will last probably another 100 years. But some of the newer stuff's not going to last that long, because we're designing a lot closer to the margins now. But yeah, you're right. There's a whole industry sector, and it's getting bigger and bigger. And it's not taught. I gave a talk years ago to the HSE in the UK and a few other insurance and regulators at a conference, and I was bringing up the fact that this whole new area is not taught. When you go to university and you do your degree in mechanical engineering, or you do your degree in whatever, it's all about design. It's all about producing new things. So you're going to do aeronautics. It's all about producing new planes. It's not about how do we keep the old ones up and running for 20 years, another 20 years. And some universities are starting to take that on. Brunel and Manchester in the UK have looked at this, and a few others in the US. So that you'll start to see, I think, in the next 10 years, degrees, engineering degrees, specifically aimed at integrity management. At the moment, it's sort of like postgraduate type of things after people have done the normal degree. If that makes sense.
No, thanks. Very, very interesting. Yeah, very interesting. Thank you.
Pak Ian, before I give back to Pak Phil, one more question from my side. What is your perspective of building information modeling, drones inspections, and also some kind of digital twins for this forensic industry?
This is probably, yeah, digitalization of this would be nice. It's finding some way of transferring the knowledge and out of people's head. It's quite difficult to automate some bits of it, but like anything in engineering, there's a lot of things in engineering that artificial intelligence might struggle with, like physically climbing up something to have a look at it. And as time goes by, that'll change. But at the moment, digitalization's tricky because they're coming in bits, they're broken. Handling them's tricky, and then having the knowledge to where should we section. It will take quite a few years because that knowledge is sort of passed on from old engineer to young engineer at the moment. Hopefully, because there's so much of it, it's not a field where people are struggling for work. It's odd in the terms that it's up and down because someone's got to fail, and nobody wants anything to fail really. So you can't predict when the work comes in or what the work type's going to be. I mean, my wife's addicted to the black box things about airplanes falling out of the sky. You know the documentaries on the Discovery Channel. My wife thinks they're brilliant. Personally, I mean, it's great. It's an interesting field where you can engage people and you can engage engineers and young people. So maybe it is an area of growth. But digitization, tricky. Not impossible, but tricky. I don't think we'll be, unless there's a change in some of the input equipment, measuring equipment. I think it'll be tricky for a while longer.
Okay, so I give this screen back to Pak Phil to give the social speech for Pak Phil.
Okay, thanks, Mary, and thanks very much, Ian. That was just to echo Mike's comments, that was a really fascinating discussion. A specialist field that you spoke about, but I thought with a lot of really good messages for all branches of engineering. Like Mike, I'm a geotechnical engineer, so I was all ears when you were talking about pipelines running up next to landslides, because we're right in the process of designing one of those here in Indonesia at the moment. So that's what's so good about joining talks like this. It gives you something to think about in your own field. From my perspective, I guess as a message to all the younger engineers, I would encourage you to read as much as you can about failures if you get the chance to find articles, and keep your own library, because it's surprising how as your career goes on, little things that you read help you become better designers. I've always done that, and this kind of lecture is another really good example. On the hardware side, Ian mentioned, well over half of the failures are due to design failures. So that's very much in our hands as designers, and need to be aware of that, as well as the importance of good construction supervision, and understanding the importance of quality installation, QA, QC. So your job's not finished when you've designed it. You've really got to make sure you're looking at how it's, the transportation side, but also how it's going to be built, and who's really keeping a close eye on that. And just finally, the other thing I liked was your root cause and your fault tree image. You can do that as a designer to help you with your checklists, as have I really thought through everything that I think could go wrong here as a designer, because if anything does, someone like Ian will be asking you, did you do everything that was reasonably possible during the design stage? So for me, there was a lot of great messages all the way through, and thank you very much, Ian. Thanks for taking the time to join us. I'm sure we all really enjoyed listening to you. I think I hand over to Ben or Mary to close.
Thank you, Phil Woodmansey, for your closing remarks. Once again, thank you, Ian Petrich, for your excellent presentation, and thank you also to Mary Natalia for guiding the session. Ladies and gentlemen, we have now reached the end of the event. You can access your e-certificate with the link on the screen or on the chat box. And for Binesian, don't forget to fill the attendance Google form. Once again, thank you for your participation. We hope we can see you at the next event. At last, good evening and stay healthy, everyone.
Thank you, everyone.
Bye.